I want you to make sure you put your phone number right here, guys, because the school wants it. In case of emergency, we got a way to contact you before you hit the school. You know, whatever happened, a couple nights ago, we're gonna make sure everybody be notified when something happens. Right, guys. I want you to look at this part. Look at the part right here. So what happened? Look at the surface finish in that part. Is that right? You might think it's polished, but it's not. To take a look at it, but this is super finish. And then this one right here is another part. So I was telling you then that I saw you in the parking lot, and where have you been? All right. Yeah, look at it. So this is another part. I want you to compare the texture, which is the roughness of the part, is the surface finish, all right? So you can see there are surfaces that are more rough than other ones, is that right? For example. And then it depends what is the parameter of the cut that we use with the shape of the tools, the materials. Many things have different, as you can see it, different, I could pass this part right here and you guys pass all over. Is that right? And since we want to do the finished surface on the fly cutters today, you probably will notice that we're looking for, if you go with your part, you can go like this and try to find it just like that, scratching with your nails. You will see how the feed affecting the surface roughness on the part. Yes. You can even look at this one right here, right? And as you look at right there, that one is very rough. This one is smooth, but not as smooth as the other ones. Is that right? This is a fly cutter. Look at the face on the fly cutter right here. Look at the shank on the fly cutters. And this one, if you look at the inside part, well, look, guys. So I want you to look at this one. Sorry. I got this one. First, it's good to understand why roughness is important. When the surface is rough, you got more contact with the air because the irregularity of the surface allows oxygen to get more into the part. And then retain water, humidity, it can produce corrosion quickly. Does that make sense? Smooth surface lasts more to get rust. Another important is when two surfaces are in contact, if the surface is too rough, they wear out quickly. So making it smooth, it maintains the surface more stronger. That's why you can see right here on this rod right there. The surfaces are very smooth because in there they need a permanent, stable feed. They don't want move in between the joints of that part. Because every time they produce this tapping, and that produce inner move inside the materials, and they release energy. Everything are made by atoms. Atoms that get together by the energy that they possess, the attraction they get. When they release that energy transforms in temperature. And that temperature makes the metal soft and they wear out or expansion. So, yeah, we control the amount of roughness. Not every part has to be really smooth. There are some pieces, for example, if you want to put a seal sometime, I remember when I was working in that company, when they cut the ball, the color rings, or the rings that goes around these big tube to put them together, they need a special amount of roughness because when they put the gasket, they want the gasket to fill that area to produce, avoid leakings on the part, or when they put compounds. Yeah. But roughness is measurement. Since they have to be a little bit, really small particles of the inches, they measure me then in a million of an inch. How many zeros are in millions, guys?
7 is it?
7 zeros? Okay. I wish they give me a
Six.
million with
6 zeros.
6 zeros.
Yeah, 6 zeros.
All right, so 1 million, right? Look, guys, if I erase, roughness is measurement bonds 1, 2, 3, 4, 5, 6 decimal places. Mean they should divide an inch in a million equal parts. It's called micro inches. They also should divide meters on a million equal parts. Yes. Well, here, you see this number right there. That number is 63. But you also see that symbol right here. This is the symbol that they put on top of the surface to specify the amount of roughness that surface has. And they tell you 63 what? 0, 0, 0, 0 millions. Let me see, 1, 2, 3, 4, 5, and 6. 6 decimal places from the point. To make sure that what I tell you here is true, I want you to go ahead and read on your book what is roughness tough, surface roughness. All right, Louis, go ahead, read that part. Page 146.
The roughness average is the arithmetic average of the absolute values of the major profile height.
That's roughen. That's roughen.
Go ahead, you read the one that we're talking about. It's not ready yet. Sign right here, Louis, put your phone number, and make sure you go right here and sign right here too. Go ahead, read it, please, Antonio.
All right. The presence of finished symbol does not guarantee any particular degree of smoothness to that surface. When surface roughness height must be controlled, figures are placed above the left leg of the finished symbol as shown below. These figures represent the mathematical average deviation from the roughness center line and are expressed in micro inches. Millionths of an inch, or micrometers, millionth of a meter. The figure 63 above the left leg would actually represent 63 millionth inches, and the metric figure 1.6 would actually represent, is that 16th millionth?
Yeah.
Meters. These figures.
Yeah, exactly. There, yeah, it's let me see. 1, 2, 3, 4, 5. 1, 2. Yeah, it's.
Okay, yeah, because the meter, and then the other one was the inches.
Right.
That's what.
It's 1 million.
Yeah, one.
1.6 millions of a meter.
Yes.
It's 7 decimal places. You see it?
Yes.
So it's just a smaller. 1, 2, 3, 4, 5. 1.6 millions of meters.
1.6
That's what it
million.
is. Is
Yeah.
that right?
Yep.
That's what they use the point right here. See? 1.6 million of a meter. 1.6 million or 0.8 million of a meter. So it's very, very small amount. They call micron. Micron is a shortcut for million of a meter. Inch, use the word micron, but have to be accompanied by inch. Micro inch. We say microns, meter. Micro inch is inches. We used to divide 1 inch in a million part. They used to divide 1 meter on a million part.
That's
We take-
crazy.
Yeah, we take more than that, and they take less than that. Does that make sense?
Yeah.
So we take a 63 million, 32 millions of an inch, because inch is a little bigger.
Yeah.
But meter, in a meter, we have, I don't know, like 90 inches, something like that. So they take one only, but it's almost the same amount. Does that make sense?
Yes.
So that indicates the amount of roughness on the part. But does every surface that we cut can be that smooth? No. Number one is you require special different type of process to obtain those surfaces, all right? Roughing, 120,000. If you go to the next page, guys, and you look at your book, right here, what they talking about? If you look in here, what is that? For example, 63 million or 32 millions. Well, it's the amount of the measurement of the irregularity looking through the microscope, a powerful microscope. Any surface that you see, when you look through the microscope, it will look like that. It's a combination of the shape of the tool bit, the feet, and how much the material is released from the part. So when the part let the material go, because the cutting force is active, and when you cut the material, sometimes you cut, sometimes they remove. And that's where you see more rough, because it won't be cut. When you have a surface that looks rough, what you gotta do is go sharpen tools. In our case right here, the tool that we have probably don't get that nice kind of finish. Number one, because the grinding wheel that we have do not produce even that finish in a cutting edge and tool bit. So, but we can combine what is a light cut. Why we use a light cut? Because when we use the light cut, it's less energy. So, for example, if you hold it like that, and somebody pushing and you strong right here, and somebody make a little portion, they go whoop, and you go like that, right? But if you're making a light cut, you hold it right here, you let them go little by little, and it's more smooth. And that happens between the material and the tool bit and the process of elaborations. The radial nose of the tool bit affecting the finish, because if we have a tool bit that have more radial nose, let me see, I want to use it right here. We have a surface right here, and we got two tool bit. We got this tool bit, the one that we use, for example, right here, and we got another surface, and we got this tool bit. If it's too big, it produces vibration. But it's not too big or not too small, something more smooth. The surface that we cut, it will be something like that. When you combine the RPM and the feed, if you go right here, the surface that you cut will be like that. When you combine the RPM and the feed. Imagine this is the part, right? And this is the tool bit, and that's the feed. Therefore, you combine the feed and the RPM, increasing the RPM, reducing the feed, you probably got the cut is more smooth because it goes more even, so it's more nice. When you increase the feed and you reduce the RPM, and in your pointing tools, you probably produce more abrupt lines on the cut than the roughing cut. When it's smooth, the lines are very, very close, very close, very close, and the whole surface will be smooth. Does that make sense? During the grinding operation that you know, not every surface produces the same amount of surface finish. For that, you gotta use the lubricants, you gotta use which is called coolants, you gotta use absorbing heat. And looking in here in this chart in your book, you probably notice that there is a legend on the bottom of the chart. You read that part? You saw it before? Just to go quickly about it. In here, they indicate the average roughness. In here is metric, and in here is inches. Right? For example, 3.2 millimeter is equivalent to 3.2 micron is equivalent to 1.25 micro inches. Is that right? Or million of an inch. And then commonly what we do. So I don't see that on my, let me see my book. Yes. And then 63 is equivalent to 1.6 micron, 63 millionths of an inch. 32 is equivalent to 0.8 micron, I think 0.8. Yeah, 0.8. Yeah. And as you notice, this is the average process that obtained that kind of surface roughness. Plain cutting is 500 micro inches, which is almost 5,000 roughness. But if you go chemical milling, they start getting better surface finish. And then if you have a lapping of electropolishing, super finishing, you notice that we have more finishing up to what? 4 millions, 8 million, 16 millions. That's super finish. Does that make sense? What do we need to know this? Well, because when you read the print, you will need to be able to identify what surface is more smooth than another one. Does that make sense? But how they place that in the print? Well, they use a symbol. For example, on this right here is the symbol that we use. The symbol that they use, you've probably seen it before, and it is like that, commonly. Commonly, they do not say what is the waviness height, what is the waviness length. Those two numbers are in inches. The waviness height is when the waviness of the cut, the roughing cut, is moved like that, that's the waviness height. And the waviness length is how long it starts taking. Sometimes it's short, sometimes it's long. Is that right? So this one make an inches. This is what is the direction of the cut. For example, to give you a quick sample of this one, you make those parallels, right? And after that, you want to grind them. If I put these parallels right here on the machine, and I use my grinding wheels to grinding these parallels, and I set them like that, and I cut this crossing like that, they will be cut perpendicular. But if I put the parallel like that, and I cut like that, the description of the roughness is parallels. In this part, that symbol means in the outside surface, the grinding wheel goes like this, or the processes go like that. But from the inside, it goes like this. So basically, it's smoother, maybe they do honing for the inside. Honing is a tool that they have like abrasive pads around the tool, and they can spread out because they have springs on it, and they put a lot of water and they move it. And they made the part perfectly smooth. For example, hydraulic piston require honing. That's what those parts are so expensive. When the part first have to be what? Have to be bored all the way in, got it, and then send it to that machine. Because during those process, how much they remove? 1,000, 2,000, 3,000. They rectify the shape of the surface, and they make the surface really smooth. That way they can produce seals. That way they compress the fluid that put a lot of pressure. Is the fluid leaking on it? They don't have no pressure on it. It don't work good. Does that make sense? Yeah. Everything, the chuck that you put in the car, they use the rubber seals. But if you don't have rubber seals to use it, then you have to use the ring. It requires very smooth surface. Same happen with the piston in your car. If your car is wear out, and the piston wear out, or the cylinder wear out, when they put the piston, the ring wear out, they let them go. So when they are smooth and it's pretty nice and clean inside, is when they produce a lot of. So what happened is those description, those symbols describe in what direction the process is due. And that number here, that's the most important number. Does that make sense? What is that number? The amount of roughness. This one is 63 watt. 63 watt.
Million?
Millions. And this one is what?
32 million.
32 million. What surface smooth? The ID or the OD? Huh? Imagine that part right there is this one right here. It's a bushing. Is that right, Luis? See that part right there? It's a bushing. If you look at this part here, hot taper. But they got really smooth finish. The outside is not as smooth as the inside. On the outside, they want 63 million. On the inside, 32. Which one's smoother?
The 32, isn't it?
The 32. Is that right? Is that right, guys? Well, there is something more that I want to show you today. This is on page 148. Every description that we talk about right now is in there. On page 150, that symbol can take a different shape. When the symbol has this, because it gives you more information on that, but not always just like that. If you go on page 150, you will notice that that symbol can be shown with the closed bar on top of that. Yes. Let me see. This is the P. Or like that. What is the difference? When the symbol shows like this, they do not specify what method of production the surface is obtained. I should read that there. This is called a basics surface texture symbols. A surface may be produced by any method of machining. You see all those methods that we saw, lapping, milling, but they don't care. They put that any method. Does that make sense? Basic texture symbols. If the symbol now show with the enclosed part in here, is you remove materials by machining only. Material is removed by machines. What is the number? If you read that in your book on page 150, I want you to read that paragraph. Go ahead, Diego. Read it loud. Reading is good. When you read it, your brain works. Is that right? Reading is good. If you don't realize it, you have difficulty reading, you have to practice more. Because some part of your brain is not making good connections. So that happened to me, so I like to read material removal allowance on the number. That is what that meaning here. Indicate the amount of stock that be removed by machining in millimeters. This is millimeter. or inches. Now it's millimeter. 3.5 millimeter is approximately 1/8 of an inch. You multiply this times 0.03739, you do it right now, how much you get? Get your calculator right there and do it. So you multiply this number for 0.03937 times 3.5, how much you get? Well, how much it is?
I got 1.37795.
1.377. It's approximately 1/8 of an inch. It's 125, a little bit more, but it's approximately. Does that make sense? Look at in here in your book. You have one without this number in front. That indicate what? You read that, Antonio?
The one that
The
the
one without the number.
the material removal by machining is required. The
Is that right?
horizontal bar.
Keep going, sorry.
The horizontal bar indicates that material removal by machining is required to produce the surface, and that material must be provided by the for that purpose.
So this bar indicated that the process had to be done by machining. Does that make sense? In the other one, they don't tell you. Whatever you get, it's okay. But this one is, so they put the number in front because that's the amount of material is required for machining. For example, you want to make a part that has a super finish and you want to let the 2,000-3,000 down, you put 2,000-3,000 in front of that. Or is a surface, is a part that will be cut, you need to let that, after that, you make a roughing cut and then the finish cut. Like we did right now in the white cutter, we let how many thousand for the finish?
50,000.
50,000. So in there would be 50,000 in front. Does that make sense? Excellent. The other symbol that we saw in here is this one right there. Look at this symbol right here means stop.
No.
No, go ahead, read it.
It says material removal prohibited. The circle in the V indicates that the surface must be produced by process such as casting, forging, not hot finishing, cold finishing, die casting, powder metallurgy, or injection molding without subsequent removal of material.
For example, this bar is casting, and then the outside surface, they want it like that. Because after that, they want to paint it. When they paint it, they got more wrapping. So you cannot smooth this one. Don't send it to the finish, super finish, to make it nice. They don't want it nice. They want that like that. You see that symbol, or if you put that symbol, nobody can touch a surface to do nothing. Not even sand it. Sometimes we use a piece like this one. That's a cold rolled steel form. We hold the part from here, we cut out those surface. If you flip it and you cut that surface, then when I put it back, I'd never get the center again. Unless I put 2 center holes. I hold the part by center. So for that reason in here, no material removal. Because when you set the part on the machine on 3-year chuck, and you take it off, and you cut the surface, that you will never get the same center again. Unless you do in a collet chuck. In order to maintain the same location, the part has to be whole between centers. When the part is hold the part, hold it, grab it, put it back. Every time you take the part out, put it on, and I put it on again, I will locate the same center. Do you understand what I mean? When the part is located between center, is you hold the center of the part. So that's why many parts, even though you don't see it, they have a technological holes at the end. Because those technological holes at the end allow when you want to do the part, you do the part in the lathe and you want to do in the grinders, the surface would be exactly concentric. Does that make sense? That's a technological process. In here, you see that angle right there? This one is 60 degrees. What is 60 degrees? Because the light center has 60 degrees. Light center for light duties are 60 degrees. Light center for heavy duty, they can be 130 or more. I think even 90. Is that right? 90. But commonly, light center here, that way you can hold the part between center. We're talking about surface finish. That same moment, material removal is what? Prohibited. Is that what I'm saying, guys? Alright, so that's a regular test symbols at the end, as you see it. And there is some examples in here, how to use it. And now, I want you to guys, let's go working now, put it right here. There's one right there. There's one. Open your book, or let me see how many questions we have in here. Let me check if you reviewed your homeworks. Let me review the homework that I assigned you guys. So, do you finish those exercise questions that you had before? Oh, you did it. Perfect. So you did this one too. Oh, I want to review all this, but you forgot this part. So go ahead and finish that one right now. What about you? Let me see what you did, brother.
I did
Partial. You got to finish that part right
this
now.
part, yeah.
Okay, you too. What about you? So what grade do you are? You didn't finish those. You have trouble. You didn't finish this one. And you didn't do that one. So you didn't do any homeworks. Nothing. So go ahead and finish this right here. Oh, let me see. First, one at a time. Finish those here. Okay? I want to review them. You have questions, let me know. Is that right?